Hello, welcome back to Unit 1. This is Part 4, and in Part 4 I'm going to introduce you to the topic of vectors. In order to understand what a vector is, you have to understand it in relationship to what it is not. So I'm going to introduce you to two concepts, the scalar and the vector. So a scalar is a quantity that has a size only. Now, in physics, we don't really refer to the size of a vector. Instead of this word, we use the word magnitude. Okay, so scalar is a quantity that only has a magnitude. It only has a size. Contrast that to a vector, which not only has a size, a magnitude, but it also has a direction. So it doesn't matter only how big it is, but in what direction it is moving or acting or going. Pick your favorite action word here. So now let me give you a list of scalar quantities, common scalar quantities, and vector quantities. So a scalar quantity is time. Yes, we can think about time going forward and backward. But we can't think about time in terms of going north, south, east, or west, right? It's not the same sort of directionality as other quantities would have. Okay. Another scalar quantity is distance. Okay. How far do you travel? If you think about being in your car, oh, and I guess I need to add another E onto distance here. If you think about being into your car, this would be just you zero your odometer when you get gas, and you look down and you see that since you got gas, you've traveled, say, 29 miles. That's the distance you've traveled. It doesn't care anything about the where you've traveled. Where are you in relation to when you got gas? It doesn't care. Okay. Speed is also a scalar. Okay. Time, distance, speed, how fast you're going. Speed. Over on the vector side, there are kind of sort of two equivalents to distance for vectors. One is position. If I want to, you call me asking for a ride, you're going to have to tell me where you are in relation to something I know. So I'm standing in front of Walmart. That gives me your position relative to something with a direction in front of. So that is a vector. Right? The other vector equivalent to distance would be displacement. Okay? So again, this is how far have I traveled from where I was, but not only does it matter the distance I've traveled, right? But we're talking straight line distance. We're also talking about in what direction. Okay? If you tell me to walk forward 20 steps, I know my displacement will be 20 steps forward. If you tell me to walk backward 20 steps, my displacement will be different because now I'm 20 steps behind where I was to begin with. Okay. Vector equivalent of speed is velocity. How fast are you traveling and in what direction? Now, you don't have to memorize or know these vectors versus scalars. We will have all of Unit 2 to get all of this sorted out. So I'm just trying to give you an idea to contrast what these two types of quantities are. Other scalars, mass is a scalar, and oftentimes mass is confused with weight. Weight is actually a vector because weight is a force, right? Force is a vector. I think that's probably enough to give you an idea of scalar versus vectors. Okay, so with vectors, all vectors have a magnitude and a direction. They can be viewed as the sum of three vectors, one in the x, one in the y, and one in the z, assuming a Cartesian coordinate system. And using our trig, I can convert in and out of, I don't want to convert here. I can find the other pieces that I don't know. So for example, if I know the magnitude and the direction, I can find the components using sine and cosine or tangent. If I know the components, I can use Pythagorean theorem to find the magnitude, for example. Right? So let's think about vector notation. So I'm going to write down an arbitrary vector. Let's let it be the vector A. Okay. Now, for a vector, there's a couple of notations you might see. When writing by hand, typically what we do is we put a little arrow above it. Okay, that little arrow says, hey, look, I'm a thing that has a direction, so watch out for me. Okay. Now, I said in the last slide that I can write any vector as the sum of three pieces. So I can write it as an piece a sub x in the x direction. Oh, what is this? This is actually, I forgot the dot. This is I hat. I hat is a unit vector. Okay, it's a unit vector. Okay, what is a unit vector? It is a little vector with a length of 1, so it doesn't affect the magnitude. So a length of 1 that points, in this case, in the x direction. As an alternate, you may be familiar with you seeing x hat. So x hat is the unit vector that points in the x direction. So these would be equivalent notations. Okay. So again, I can write any vector as the sum of three pieces, one in each direction. I've got the x piece written down, and now I can write an AY in the j hat direction plus an AZ in the k hat direction. Okay. Or down here, you may be familiar with this notation, where everything you see with a little hat over it is a unit vector. A little vector, the length of 1, that points in a particular direction. Okay. Okay, so that is the notation we're going to be working with. I will endeavor to work in I, J, and K and try to keep things consistent for you this semester. If I slip, I am sorry. So let's think about this for a minute. Can the magnitude of a vector ever be equal to one of its components? So can the size of the vector ever be equal to one of its components? Well, remember, I can find the magnitude of a vector using the Pythagorean theorem. In this case, I would have to use a three-dimensional version of it. But I can find the magnitude, absolute value signs indicate magnitude, of my vector A by using Pythagorean theorem. The three-dimensional version of it. So can the magnitude of a vector ever be equal to one of its components? Yes, as long as the other two components are 0. Okay. Can the magnitude of a vector ever be less than one of its components? I think from here it's pretty obvious that the answer is no. There's no way that A can be less than AX. It can certainly be greater, but it cannot be less. Okay. Let's do an example. And in that example, we're going to deal with a two-dimensional vector just because it's easier to write and draw and think about. So I'm going to define a coordinate system. X and Y. I'm told Vx is 6.8 and it's positive. So I'm going to come over here and say right there is 6.8. Right. Might as well. Vy is a negative 7.4, so I'm going to let this be Vy. So this would be Vx. Oops. This would be Vy. And V is down points from the origin down to here. So now you can see the triangle and why Pythagorean theorem comes in here. Okay. So V is on the hypotenuse, so V equals the square root of Vx squared plus Vy squared, which is the square root of 6.8 squared plus negative 7.4, the whole thing in parentheses, so you got to square that negative sign as well. Okay, so 6.8 squared plus 7.4 squared. Take a square root of that, and I get that V in magnitude is 10.05 units, whatever they happen to be. Okay, so that determines the magnitude. To determine the direction, I have to define an angle. So I'm going to define this angle right here. Now remember, in polar coordinates, the angle is always measured with respect counterclockwise from the positive x, as we saw in the last unit. For this sort of activity, you just need to define your angle. So here I've defined this angle theta, and now I can do tangent of theta. Now technically, I could use any of the trig functions to find this angle. I am choosing to use tangent because that's based off the information I was given, and it's not going to result in round-off error, for example. It's also not going to be impacted that, if I accidentally put something into my calculator wrong when I did this calculation, then if I used V as the hypotenuse, it would carry forward. So it saves me from that sort of error as well. So I prefer tangent. So tangent theta will be negative 7.4, which is my side opposite, this length right here, divided by my side adjacent, which is 6.8. Taking the inverse tangent of that, assuming I can punch into my calculator, gives me an angle of negative 47.4 degrees. Why is it negative? Well, there is a sign convention for angles that counterclockwise from positive x is positive angles. We are going counterclockwise. Oh, backwards. We are going clockwise, therefore it is negative. If you gave me this picture and that angle, I would be fine. If you were to tell me that theta equaled 47.4 clockwise from positive x, that would also be sufficient. I guess I should make that look like a 7. Okay. My apologies. Sometimes the tablet does not do my handwriting any favors. Okay. Lastly, it is common for students to get into a rut, into a habit. And that habit is that the tangent of an angle is the y component, we'll go back to ay, divided by the x component. This statement is true if I define theta with respect to the x-axis. So ax would be the x projection of that. Ay would be this length over here. So ax plus ay equals a. Life is good. That is true. Ay over ax. But angles are not always defined with respect to the x-axis. If, on the other hand, I were to define this angle, probably should label my axes here. If I were to define phi, then if we look at phi, the side opposite is the x component. So the tangent of phi would be ax over ay. And if you were given phi and used that to manipulate things, you'd end up with a wrong answer. So rather than memorizing that tangent of theta is y component divided by x component, what I would prefer you do is memorize that tangent of theta is opposite side divided by adjacent side, and then always draw a triangle and check out which component is on which axis. 9 times out of 10, it's going to be y over x. But that still leaves the 10th possibility. And on that note, this concludes this part.